If you would, it would be helpful if you had an equation sheet out also and your calculator. If you need to borrow an equation sheet, please do. We are going to start off today with just a little bit of vocabulary, okay? And we are going to get started into the math of this chapter. We're going to start very simply with the simplest type of problem, and we're just going to gradually work our way up in difficulty, okay? So let's start off with just some vocabulary terms that you're going to come across in the next two chapters. Okay, what does the prefix poly mean?
Numerous.
Many, multiple, more than one. Okay. Let's just refresh our memories on our latest definition of what an acid is. An acid is something that gives away hydrogen ions. You can also call them protons. Remember, they're the same thing. An acid is a proton donor. So polyprotic, more than one proton to give away. Okay? If you have more than one hydrogen ion to donate, that is a polyprotic acid. If you want to get more specific, an acid that has two hydrogens you would describe as diprotic. 3, triprotic. There is no such thing as a tetraprotic. Okay? What would you call an acid that has only one hydrogen to give away? Monoprotic. Most of our acids are monoprotic. Okay. So an oxyacid, that's a term you have seen before. It's exactly what it sounds like. It's an acid that has oxygen in it. Okay. And organic acids, which we will deal with more at the end of the year, they still have a hydrogen to donate, but these are acidic hydrogens connected to very long carbon chains. They are generally very weak acids. We'll deal more with them when we get to the end of the year. Here's another term you need to know. Amphoteric. That means something that can behave as an acid or a base. Let's refresh our memories on the definitions here. Something that can donate a hydrogen ion or accept it. Okay. Water is an example. Okay. And this reaction is showing you exactly that process. Okay. Some waters can accept a hydrogen, and if they do, this is what it turns into. Do you remember the name of that? Hydronium. Okay. If water gives away a hydrogen, it turns into hydroxide. And guys, any sample of water that you drink, cook with, whatever, okay, it's not just H2O. You are also ingesting H3O plus and OH minus as well, okay? It's good for your body to have these ions. Deionized water means there is little to none of these, okay? Deionized, no ions, okay? Then it would be pure H2O. All right, and let's just review some vocabulary that we saw at the beginning of this chapter. If one of these waters is acting like an acid, giving away a hydrogen, whatever it turns into is called your conjugate base. If the other water is acting like a base, when it accepts that hydrogen, whatever it turns into, that's called its conjugate acid. Okay, and I said before, particularly in multiple choice, you'll have questions where a reaction is written out, and they will just say, what is the conjugate acid in this reaction? And we need to remember its definition. Now, what does a capital K mean in chemistry? Equilibrium constant. We've had a lot of K's. If you feel like you're going to get all of these different K's mixed up, don't fret. Look on the front side of your equation sheet. On the right-hand side, middle, it says equilibrium constants, and they are listed there. And in parentheses, it tells you the situation where you would be using them. Okay? KC and KP, we use those at the beginning of the year, back in first quarter. KW is to be used with this equation only. And Ka is used with acids, weak acids. Kb is used with weak bases. Now tell me this. If this is an equilibrium expression, and all equilibrium expressions are products divided by reactants, how come there's no denominator here?
Liquid.
Yeah, the reactants are liquids. Liquids get excluded. What else gets excluded? Solids. Okay? So my Kw expression, which will always be this, remember, guys, H plus is just a shorthand way to write H3O plus. They mean the same thing. Okay? Kw also always equals that number. Don't memorize it. It's over on the left-hand side. There is a section on your equation sheet over on the left-hand side that says equilibrium. Every equation you could possibly need is there. There will be very little memorization, little to no memorization in chapters 14 and 15. Okay? Now, okay, Kw always going to equal 1 times 10 to the negative 14, okay, at 25 degrees. And I just want to make sure you are aware what these terms mean. If you say that something is neutral, what kind of a pH are we talking about?
7.
pH of 7, not 0. pH of 7. And if something is neutral, all that really means is that your hydrogen and hydroxide ion concentration, those molarities, are equal. That's what it means to be neutral. What it means to be acidic, and by the way, what kind of pHs are acidic?
Below 7.
Yeah, less than 7. Okay? All that means is that the concentration of hydrogen ion is greater than hydroxide. And vice versa for a basic solution. Okay? So I just wanted to make sure you were aware of that situation. Now, the number one thing you're going to be asked to do with pretty much every problem for the next month is to calculate a pH. You can't calculate a pH unless you know the hydrogen ion concentration. Okay? This equation you are going to use more than any other equation for the next month.
Do we memorize it?
You do not need to memorize it. It is on the left-hand side. It's the 1, 2, 3, 4, 5th line down. Okay? Make sure you take note that is a log base 10, not natural log. Okay? And I hope from Chem 1 you remember that there is a pH scale. There is also such a thing as a pOH scale. By the way, does anybody know what pH stands for? It does stand for something.
Hydrogen substance.
What is it? You're very close. Presence of hydrogen. The presence of hydrogen. So this one would be the presence of hydroxide. Okay? Now, I'm sure you all remember your pH ranges from 0 to 14. However, we're going to see in just a minute that there is such a thing as a negative pH, and there is such a thing as a pH above 14. Okay? It's just that most acids and bases fall in that range. Okay? This statement should make sense to you. As the pH decreases, getting closer to 0, are we getting more acidic or more basic?
More acidic.
More acidic. Okay? As pH decreases, that means more acidic, hydrogen ion concentration is increasing, not linearly, but exponentially. Okay? Now please don't shoot the messenger. I hate to be the bearer of bad news, but pH has its own rules for sig figs. It's not hard, but let me explain it to you. Let's say that I gave you a very easy problem where I gave you a hydrogen ion concentration and said, calculate the pH. Fine. You would take this number, put it in right there, negative log of, hit enter in your calculator and the number 8 is going to come up. Do not write pH equals 8. Do you agree that this given piece of information, and that's always where you get your guide on sig figs, from given information, do you agree that this has 2 sig figs?
Yes.
Okay. When you go into the realm of pH, the only digits that are significant are the ones after the decimal point. So if your original number had 2 sig figs, that means your pH needs to have 2 decimal places. Okay? And vice versa. What if I gave you pH like this, 11.316, and I said solve for the hydrogen ion concentration? How many sig figs should your answer have? 3. Okay? So it goes both ways. Okay, this is just showing you some relationships here. pH 0 to 14. Your pOH scale, guys, is exactly the reverse. If something has a pH of 1, it has a pOH of 13. Okay, this is the relationship between your ion concentrations. So here's the deal. These 4 relationships, none of which you have to memorize, they are all on your equation sheet. Knowing these 4 equations, I could give you any one of these pieces of information, and using a variety of these equations, you could solve for the other 3. And that is exactly what I want you to do. So for example, in number 1, I have given you a hydroxide concentration. I want you to solve for pH, pOH, and H+ concentration. There are multiple avenues in which to get to the answer. As long as we end up in the same place, I don't care how you got there. Go. There is one particular step that I want to just make sure we're all clear on how to do. Okay. In number 3, the information given was a pH. I just right off the bat wrote out what the pOH is. How did I get that number?
14 minus.
14 minus the pH. Okay, great. 6.59. I decided the next thing I wanted to solve for, and you could have gone in a different order, I decided the next thing I wanted was the hydroxide ion. And I wanted to use this equation right here. I had the pOH, I had to solve for that concentration. How do you, I don't know if I'm using the right word, how do you invert a log? Jess? Okay, in your calculator, if you do second log base 10, not natural log, what you'll see come up in the screen is 10 to the power of. 10 to the power of what? Be careful. Negative. Bring the negative over. 10 to the power of negative 6.59 gives me that answer. Okay. We're going to start, right now, we're going to start learning how to do a little bit more complicated pH calculations. We're going to start off just a little bit more complex. For those of you that have the slides, this slide and the next one have a list of steps, things to consider when you're doing a pH problem. I don't want you to cross them out because I do want you to have these things. But without an example in front of us, these steps are kind of meaningless. Okay? So I'm going to jump to a sample problem. However, this statement I cannot emphasize enough. In chapters 14 and 15, there really are no two problems that are the same. You can't memorize a way to do them. You must understand the chemistry if you have any prayer of doing these problems. Okay? That's why I'm going to go a little bit slower, and I'm going to make sure that things are very clear. Okay? So you've got to know the chemistry. Every problem is different. So let's start out with our simplest situation, which is you are given a strong acid and asked to find its pH. Fine. Okay, first of all, how many strong acids are there?
6.
6. Imagine a perfectly clear, breezy summer night. Okay? Remember what it means to be a strong acid. Okay? That means the acids completely split apart, dissociate when you put them in water. Alright? And the wonderful thing about strong acids, the things that make them such easy problems, is this statement right here. Okay? We just were using this equation that is on your equation sheet. You cannot find a pH unless you know this, the hydrogen ion concentration. What makes strong acids so easy, let's say we've got HCl as an example. Okay. What makes it so easy is whatever the starting concentration is for the acid as a whole, let's say it's 6 molar, your H plus concentration will also be that same number. And I want you to understand why. Acids, strong acids completely break apart. Close to 100% of every HCl molecule is going to split into H plus and Cl minus. Okay? Whatever you had in the beginning, it is almost all going to be converted into H plus and Cl minus. These are very quick, easy calculations to do. It should make sense to you if we're dealing with something that is very acidic, that OH minus would be a very small number. Now, there is something you have to be careful with. This is not going to come up very often. but it does come up on occasion. Let's say we're dealing with a different strong acid, HBr, and instead of a number like 6 molar, you're handed a bottle of hydrobromic acid that has this molarity. Is that a very concentrated solution? It's the opposite of concentrated. Dilute. This is an exceptionally dilute solution. Okay, well the next thing I'm going to say to you applies to strong acids only. That's why it's on this slide. If your concentration of your strong acid is so small, how small? Smaller than 10 to the negative 7th, then what you say is, this acid is no longer the dominant acid. What do I mean by that? It is no longer the dominant donor of hydrogen ions. It is in fact giving away so few hydrogen ions that water is a stronger acid than that one. And guess what, guys? If water is the dominant acid in your situation, what do you think the pH is? 7. No calculation required whatsoever. Okay? Let me just say it again. And this is for strong acids only. So you get a problem, you see HBr and you recognize, yep, this is a strong acid problem. The next thing you should do is look at the number. Again, this is not going to come up very often, but it does on occasion. If that molarity is smaller than 10 to the negative 7th, this is not the dominant acid. Water is in fact the dominant acid, which means your pH is 7. So, let's do a really quick problem together. These are super duper quick. Calculate the pH 0.2 molar HCl. Strong or weak, this acid? Strong. Now look at the molarity. Is it smaller than 10 to the negative 7? No. So that means HCl is my dominant acid. And I can use this equation. What is my hydrogen ion concentration? 0.2. Plug it into your calculator. Negative log of 0.2. Tell me what you get. 2 sig figs, which means 2 decimal places. 0.70. Would you say that's acidic? Yeah. That's pretty acidic. Okay. Let's do another one. Calculate the pH. Look at the acid. Strong or weak? Strong. Now look at the number. What's my pH?
7.
The pH is 7. How would you explain why? Water is the primary donor of hydrogen ions. You could also say water is the dominant acid. Yep. Second question, pH of 7. Done. So when you come across a strong acid, you should be doing a little mental dance of joy because it's a quick, easy, fast problem.
Weak acids.
Weak acids, however, a little bit longer, not significantly longer. We're just sort of gradually ramping up the complexity here. Okay? On the previous slide, did we ever use a Ka value? No. Remember when we started this chapter, I had you get a textbook and we saw that chart of Ka values. They were an indication of how strong the acids are in comparison to each other, but they're for weak acids only. That's the only time you deal with Ka values. Okay. I'll explain what I mean by that in just a second. Alright, and this is another situation that is not going to come up very often, but does come up on occasion. Alright, for strong acids on the previous slide, once you decided it was a strong acid, you looked at the molarity number. if it was less than 10 to the negative 7th, then the pH was 7. Well, for weak acids, you don't look at the molarity. You look at the Ka value. So let's say I give you a problem, and I'm just making up this number, and I give it to you as that. What does Kw equal? It's on your equation sheet.
1.0.
Okay. You want to, for weak acids, that's why it's on this slide, you compare Ka versus Kw. Which one is bigger? Ka. If Ka is bigger than that number, that means your acid is the dominant acid. And you have to do a calculation, which I'll show you in just a second. If you had a problem like this, compare your Ka and Kw, which is bigger? Kw. That means water is the dominant acid, pH of 7. I can't stress enough, this is not going to come up very often, but it is just something to be aware of, because on a very rare occasion you will be tricked. And you're going to do this lengthy calculation when really the pH is just 7. Now, do you remember these? I hope you liked them and remember them. It's okay if you don't remember them, but if you do, I hope you liked them because they are your life for the next month.
No.
If you didn't like them back in chapter 13, I hope that you will come to appreciate ice tables because they are a wonderful way to keep your numbers organized. And this chapter is hard enough. Any little thing that helps is a good thing. We are going to do the first problem together. And I don't care how cool you think you are or what a superstar genius you think you are. Whatever I write on the screen, you write. Got it? All right. Here we go. All right, it says calculate blah, 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 blah of 2 molar acetic acid. Stop right there. Strong or weak? Weak. Okay, you probably could have guessed that it's on that slide. It says weak at the top. Okay, it's a weak acid. Here's another clue. I give you a Ka value. You're never given Ka values if the acid is strong. All right. Is this Ka value small enough that water is the dominant acid?
No.
No. Okay. Here we go. The very first thing that we are going to do is I'm going to take whatever that weak acid is, and I'm going to react it with water. Okay? Now, this is an acid. What do acids do? Give away protons. Give away their hydrogen. If this acid gives away that hydrogen in the front, what's left? What's left of it?
Acetate.
The acetate ion. Hold on. And if water accepts that hydrogen, what does it turn into?
Hydronium.
Hydronium. Okay? Great. This is the reaction that is taking place. Underneath this, I'm going to set up an ice table. Do you remember what the letter I stands for?
Nope. Initial.
Initial. Initial what? Molarity. Okay? If I scroll back up to the top of the problem, it says it's 2 molar. I'm going to squiggle through that column. Why?
It doesn't apply.
Why not? Why am I ignoring water? I don't care about it at all.
It's a liquid.
No, it's not. There's something.
It's a
I
liquid.
just said this.
It will not be in the equilibrium expression, so ignore it. It doesn't matter.
And this.
Are the other ones acidic?
Hold on. Hold on. Yes.
Acetic acid, isn't that vinegar?
Yes.
So wouldn't that also be a liquid?
It's aqueous.
It's aqueous. It's something dissolved in water. Okay? Do you see any other molarities besides this other one given? Any other molarities? No. So what are these? No. They're aqueous. What are their initial molarities? 0. Do you remember what C stands for?
Concentration.
Change. Change. This was the line where we put x's. Minus x, and on the product side, plus x, plus x. Now, back in chapter 13, this is a long time ago, but I said to you, usually the reactants will be decreasing, so you put minus x, plus x, plus x, but sometimes it does go the other way. What's nice in chapter 14 and 15, we're not going to have to deal with that. They are always going to go forward. Okay? What does E stand for? Equilibrium. All I'm doing is just writing what the concentrations of these things are at equilibrium. Do you remember from way back what we did with these things? What did we do with them? Plug them into a what?
Equation.
What kind of equation?
Equilibrium
An equilibrium expression. And before I plug them in, let me write what that expression is in the first place, without any numbers. Products over reactants. Now let's plug in these values on the equilibrium level. X times x, x squared, over and we were given a value for Ka. In chapter 13, just like we're going to do here, the goal is to solve for x. Remember how we did it? Algebra, you could. It would take you a little bit longer. What's the fast way? More specifically, graph it. Okay? So let's just review, guys. Let's go back. On your calculator, go to y equals. In y1, I want you to put that Ka value. Put that number in for y1. I'm doing this right along with you. In y2, put this entire expression, and might I recommend, like I did way back in first quarter, your calculator just likes it. It makes your calculator happy. Put parentheses around the numerator and around the denominator. And hit graph. Ladies and gentlemen, it does not matter if you can't see the graph at all. It doesn't matter if you can't see the intersection point. It doesn't matter. From here, second, hit the trace button. Calculate. What do you think I want to calculate? the intersect. So we're going to be number 5. Don't move the cursor. Enter, enter, enter. Do you remember this?
How silly. This is fun.
That's what you should get if you did it right. Let's talk about what the ultimate goal is here, guys. We're trying to find a pH. What do you need to find a pH?
The molarity of
Molarity of what?
hydrogen.
H plus.
H plus.
Okay. Do you remember that H3O plus and H plus represent the same thing? Okay. Isn't the concentration of H3O plus that number? That is my H plus concentration. How do you get a pH from here? What do you do? Negative log of that number. 2 significant figures, which means 2 decimal places. What do you get? Okay. Now, if you actually read the original problem, it says to calculate a whole bunch of other things. I want to just focus on calculating the pH. And I'm going to ask you a question that you are going to get so sick of me asking, but it is important. Does that answer make sense? Think about what the situation was. It was an acid. Where should the pH fall?
Below 7.
Somewhere below 7. It doesn't matter where below 7. Don't worry about that. Does that make sense?
Yes.
Yes. If you got an answer like 9.22, you should say, I've done something wrong here.
So hydrogen.
All right. Do that one on your own. I don't care if you think you don't need the practice. You need the practice. Do it. Go. You know I'm going to ask this because I'm going to ask you this every single time. Does that pH make sense? Yes. Again, don't worry about where is it between 0 and 7. Just, is it in the acidic range? Yes, it is. Okay. Please don't worry about ever not having your calculator. This is always going to be in a free response kind of setting. I want you to look at this problem. Calculate the pH of a mixture, not just one acid, but 2. All right, well, let's assess the situation. Strong or weak? Weak. Strong or weak?
Weak.
Okay. You have 2 weak acids. In your mind, you should be thinking, okay, weak acid means I'm going to need an ice table. It does not mean you need 2 ice tables. No, no, I say to you, look at these 2 Ka values. Which acid has the bigger one? HF. Okay? That means in this mixture of acids, even though they're both weak, this one is a little bit stronger than that one. This one will be donating a little bit more hydrogen ions than the other one. The good news for you is that means you can deal with just the stronger of the 2 and completely ignore the other one. Pretend it's not even there. It's not that this acid isn't giving up some hydrogen ions, it is. But it's giving up so few in comparison to this one that when you round for significant figures, this one is not making a contribution. So, you tell me, you have a situation with a 1.2 molar HF solution, and you're supposed to find the pH. How do you do that? Ice table. Yep. This is the last thing I'm asking you to do today. Do it. Get the practice. What?
You just did this.
You literally just did the exact same reaction.
Oh, what's it?
So if you want, yeah, the only thing that's different is the molarity. So for those of you that are quick thinking, you can literally just go straight into your calculator, and all you have to change is that part of it, the molarity part. I, however, am going to write the whole thing out because I am a good little chemistry student. Let me just recap this for you, because you are going to have problems that present you with not just one acid, but 2 acids, okay? If you have a weak and a weak acid mixed together, the one with the larger Ka value is the one you deal with, and you can ignore the other one. What if you were given a solution that included a strong acid and a weak acid? You go with the strong acid and ignore the weak one. And strong acids, go a couple of slides back, those are the quick, easy problems.